let's go a little other hyperparameters. So I'm not going to talk about these today. We'll talk about this actually tomorrow's study group. And so this is basically optimizing our neural networks. Like we'll talk about some other hyperparameters. So one thing, I don't know, I did that, is learning rate. So there's learning rate, number of epochs, batch size. Remember, hyperparameters are just about, what defines a hyperparameter is basically, it's the thing that you modify for the machine learning algorithm to learn more, right? So technically, structure of like the neural network, so if we have more hidden layers, that is a hyperparameter saying, you know, what kind of things we're doing. But the classic ones that we'll tend to modify the most are the learning rate, which is basically how big of a step do we take in gradient descent, which is going to be part of backpropagation. Number of epochs, also pronounced epochs. I'll say epochs. I think it can pronounce either way, but basically epochs are saying how many times you're iterating, saying you feed your inputs through the network, you know, with the weights given, you see how bad, you say like, oh, like based on the loss function, or really the cost function, see how bad it does overall. It's like, it doesn't do very well. Send it back and it propagates that error backwards. And then you run it again and you keep modifying and running again. That's the number of epochs, basically how many kind of iterations you're going through. And then batch size, which we'll talk about again, you know, tomorrow, is basically saying how many data points we feed through our network before trying to, doing the backpropagation, seeing how bad it is. So this is a little subtle and we'll talk a little bit more, but basically the idea here is that instead of sending all, so you have like 1 million data points, instead of saying all 1 million data points through and then figuring out how overall their error is and sending it back, which takes a long time with backpropagation, instead you take like a small handful and say, all right, feed these through and then do the propagation backwards, and then you get a new handful and feed this through, go through there. And so how big your handful is your batch size. And this can actually help in speeding up your algorithm. So even though it's technically less accurate because you're only doing a little bit at a time, it turns out this is actually a really nice parameter that you can speed up your training, but you can still get relatively accurate results because it's going to eventually see the whole data set. So we'll talk more about this again. But just know that those are other parts of the neural network itself. Okay. So those are different parts. And then we say, all right, training, right? So our training is basically, you can remember it's just being like learning, right? Let me move this, there we go. So our training part is basically backpropagation. And so backpropagation, I'm not gonna like go through the whole like, you know, calculus part of it, mostly because I don't think it's necessary for you to like really like, oh, I need to pull this, you know, backpropagation out of the back of, you know, out of my head, you know, either for an interview or just for real practice even. It's important to understand like, you know, why it's doing these things. But the idea here, I think, again, 3 Blue 1 Brown, that 4th video with backpropagation calculus, he kind of has it really well, is that basically the idea here, we feed all of our inputs in, we see how well it does, or really how bad it does based on the cost function. And then we're going to adjust them, say, okay, we're going to adjust it in this direction. And that adjustment is going to be based on gradient descent. Basically, what's going to be the optimal, the optimal amount of change. Essentially, are we going to turn up the neurons up? Or are we going to turn the neurons down? We're just going to need to be more positive or more negative. And essentially what we're going to do, we're going to propagate those errors back throughout the neural network, adjusting the weights as we go through. And then we say, okay, looks good. Let's try again. And we run the neural network, what we call the feed forward process, right? And see how well it does, which it should, you know, in theory, do a little bit better, right? And say, okay, it did better, but not quite. And then you propagate that error backwards. So again, this is the main idea of backpropagation algorithm. Note that there is no like backpropagation like in the neural network. It's actually a process, just like gradient descent. The gradient descent basically is just telling us how to move it. Backpropagation is just saying we're following the chain rule of saying how we should modify each part. Okay, cool. Yeah, any questions about backpropagation in general? Sometimes I think this can feel very confusing, but I think in general, if you think of it like you just feed the data through, see how bad it does, you're like, okay, it's going to be this bad, and we're going to propagate that error backwards, adjusting the weights as we go, and then try again. Cool. Yeah, if I would strongly, again, if you haven't watched all of that video, or you kind of like, you know, played in the background, like you watched it, but maybe not watched it directly, I think he does a great job explaining it going through. Okay, so this definitely, if there's more questions, we can definitely talk about it for next time, for sure. Okay, so we're like, all right, here's all the parts, you know, here's all the pieces. You're like, cool, like, are we going to do something with it, right? So one thing to note is that before we actually start doing anything with it is that if we have something that's more complicated, we're just going to need more layers. And note that this is kind of an interesting fact for neural networks is that if a neural network is can approximate like any continuous function. This is actually from the, what's it called? The universal approximation theorem. So the idea here is that you can actually design a neural network with as many layers you want, or not layers, but nodes and stuff like this. And it turns out you can actually approximate any linear function you want. However, note that if you make it more complex, you have some dangers. If you make things more complex, you mean you have a higher danger of overfitting. You also will tend to have to train your neural network over time. So note that the universal approximation theorem says you can technically do it. It doesn't say how long it's going to take to train. It could take nearly an infinite amount of time to actually get to a level of finding the right thing to approximate that thing, but it's technically possible. Okay. Again, this is why we want to do more complex, increases chances of overfitting. It takes more time. Okay, and we'll talk about how to avoid these things next time.